This is the first class on lecture number 9. Lecture number 9 is the last lecture in the so-called part 4 that was related to local area networks. In this part, what we did so far was we went over logical link control. That was one lecture, very short lecture. Then we talked about Ethernet and other legacy LANs, which is 802.3, 802.4, and 802.5. And then we went over lecture 8, which was the so-called fast Ethernet and other related technologies. These are the technologies which evolved after the big success of Ethernet and includes 100 megabit per second Ethernet, different variety of that, and ISO Ethernet, which was for voice over Ethernet, and gigabit Ethernet. Also, we talked about VLAN and full duplex as two tricks that they were playing with the packet format. But most of the complexity was in the physical layer to go to higher data rates. Lecture 9 is related to the other fast LANs. Other fast LANs includes 100 VG any LAN, FTDI, and ATM LAN, or LAN emulator. So that's what we want to cover for today. But meanwhile, I think last week we added these interviews, a series of interviews. I don't know if I talked about it in the last lecture. I did. So there is a total of 3 interviews, actually, which are available in there. They are not bad to listen to. Each may take about 5 minutes. With that introduction, I can now go and start my lecture number 8 and number 9. Material in this lecture, just like other lectures, a good part of that are coming from the current Stallings book. There are a few like graphs which are coming from the previous edition of the book, and some which are coming from Tannenbaum's book. So I just go over the figures and I collect them, and then I build up the lecture around that. That's how I do it. What we talk about, as we said earlier, is 100 VG any LAN. 100 VG any LAN is something that started around 1995, and at the same time that people started to go to fast Ethernet. So if you remember, up to like middle of 1995, we had 802.5 is still competing significantly with Ethernet. So as soon as they wanted to go to fast Ethernet, people in the 802.5 community, which is the token ring community, they tried to go to the same path. But since most of the market was in the Ethernet, they first came and joined 802.3 community. Okay, and I have mentioned this thing several times in the past, that this is the pattern that will happen. When there are two competitors, one of them gets more successful, the other one starts. But the idea in here for 100 VG any LAN was that to design a 100 megabit per second LAN which covers both Ethernet and 802.5. So as a result, it makes sense to start in 802.3. But as they went a little bit along to find the technology, they ended up to a new MAC. And if you go to a new MAC, you have to change your committee. So rather than having like 802.3, I don't know, AZ or whatever, they went to 802.12. Okay. The other LAN that we have again discussed about it several times, we have mentioned that several times, is FTDI. FTDI is the first fast LAN, if you want to call it, which started in mid-1980s. In mid-1980s, you have to remember the hype in the telecommunication industry was what? The hype was fiber. at that time. Fiber has several times has come up as. But at that time, the hype was that fiber is going to be everywhere. Okay? So starting from the backbone, they wanted to come to the home at that time. Then the third LAN is ATM LAN. ATM LAN started in mid-1990s. And that's the time that hype was ATM. Everybody thought that future is ATM switches. Okay? So we go over these three technologies because they give you a wider perspective of fast technologies. In particular, ATM LAN is what? A connection-based LAN, while the others, everything were connection-less. So as we discussed that again one time earlier, this time we have a little bit more detail on that, how they implement it, how they implement a connection-less service over a connection-based network. That's ATM LAN. Okay. So for the 100 VGNE LAN, we go over the details to some extent, and FDDI the same. But you have to remember that the physical layer of the FDDI is the same as 802.3, I don't know, Z or whatever, fast, like 100 base X Ethernet. Okay, that's the same physical layer. So it's only MAC layer and also how they handle priority. This issue of priority, there are two issues which are very important actually and very current. One is the issue of addressing, that we had a little discussion with one of the students last time after the class. It's a very, very important issue. Because in connection-based and connection-less, we have different addressing modes. And then in local and wide area, we have different addressing modes. And then on top of that, we have a new trend of addressing for mobile application. So maybe actually it would be a good idea that one time, next time when I teach this, I put like one lecture on addressing. But the addressing itself is a topic for the networking. And another issue which is also a good topic is the issue of quality of service. Because the meaning of quality of service has been around in different manners. And there are different mechanisms which are related to quality of service. And it never dies, it's around. Okay. But it has different phases. For example, if you go in different standards, like when they have the MAC layers in 802.4 and 5, they have some priority. We call it user priority. Then you go for the access mechanisms. Some of them, they have priority in there. For example, in FDDI, we will see that a little bit later. And then you have a sort of classification of applications, like different classes of application, like supervisory, then voice, then video, then data which is controlled, data which can be in the background. So they have different classes of, if you want to call, applications. And then you have to relate all of these things together. If you want to relate them, anything which is out of the standards activities is not good enough for me to think about it. But 802.1d, okay, which works on the bridges, tries to classify these things and provides tables to relate these priority schemes to one another. So anybody who wants to go to a new standard activity goes to 802.11d somehow to be in their tables. Okay, so we talk about that when we talk about bridges and routers a little bit more. Okay, but why did I discuss that in here was that when we go to FDDI, for example, I talk about how they implement the priority. When we talked about 802.5, I talked about how they implement the priority. Implementation of the priority is one of those methods to enforce quality of service, which is yet vague. Everybody talks about it, but it's yet vague for connection-based, connection-less. And connection-based really have not came to the users. Users, all of them have, for the data application, have connection-less. The only connection-based user application is through the telephone calls, when it's wired. And if it is wireless, then they have both voice and data, like ISDN. Okay, but anyways, so we talk about here and there, when I talk about different things, if they have some algorithms for priority, I go over that, and I keep it. Because it's good to know a little bit about those priorities for the future. Though the standard is that. Okay. Anyways, with that introduction, let me just start with the first part, which is 100 VG any LAN. 100 VG any LAN is also called Demand Priority Access Method, DPAM. DPAM is the name of the MAC, okay, that they use. It's an extension of Ethernet to 100 megabit per second, very similar to 100 base T, but in here they want to accommodate both 802.3 and 802.5. It operates on Cat 3 and 5 and unshielded twisted pair's. As I said, it's a new MAC, and the new MAC is not CSMA CD, so in 1995 they moved to 802.12. All of these things were said before. Now, advantages of the DPAM. DPAM, since it is token ring, it has some sort of deterministic control over the information. It's not like Ethernet. Okay? It's like a sort of TDMA. So you have some control. If you have controlled environment, it's better for what? Time-bounded information, they call it. Now, suitable for multimedia for the same reason, because it has embedded priority in it. And compared with fast LAN, it may have a little bit more throughput and operates over all the mediums that fast Ethernet works on that. So on the paper, this is a standard which is superior to what? To fast Ethernet. But how come it didn't work? How come it didn't capture the market? This is the question that often we don't know the answer wherever we go. But if we want to make up an answer, that's a matter of opinion. The one that I always like is the one that says they lost the window of time or the cost was expensive. These are two things which comes always very early, very easy into the thing. Anyways, if you want to connect a 802.5 to another 802.5, you don't need to have like 802.5 protocol in between. You can have Ethernet in between, and at the end have two other bridges. So what this guy wants to do can be done with the bridges and fast Ethernet as well. But anyways, they had products developed for 802. I mean, DPAM had product. I mean, companies like 3Com, Cisco, they had product on that, but they never sold enough to maintain the production. But anyways, and still I think they do have still available. Now, disadvantage of the DPAM could be that it's more complex because it's token ring. Possibly yes, possibly no. But does not support full duplexer operation. That's certain. Okay. The priority that you have in DPAM is similar to the priority that you have in token ring. When you want to transfer from one LAN to another LAN, and in between you have a bridge, that priority gets damaged. For example, if you want, in one side you have like priority in the LAN, which is like DPAM. At the other side, you have Ethernet. You cannot map it anyways. So you have to lose your priority. Okay. Beyond that, when you go to inside the bridge has, again, queuing and has its own, in fact, additional delay, which gets added to the packets which arrives. And when you bring that additional delay into the operation, it would be difficult to preserve the priority. Because every packet which goes in may suffer so much of delay if the bridge is not prepared. Okay? And for so much of delay, you cannot support that quality of service or that priority anyways. Okay? As a result, it's a general belief that priority doesn't pass through the bridges. Okay? Then there is a, except HP, only a few other companies shown interest. So at the beginning when they started, they were a bigger group, and gradually everybody, and the major one was IBM, which was the supporter of 802.5, they backed off from the standard. Again, this type of trend is very popular when the standards grow. At the beginning, there are good groups, big groups, and suddenly from 100, they go to 5. Okay? It changes throughout the time. And it has happened again many, many times. Okay. Another example is wireless ATM forum, for example. At the beginning, they had like 100 people. And in a matter of 3 years, they had almost nobody. Just like 2-3 people. So, but still some people, they carry the flag for different reasons. But anyways, so this is about the DPAM like introduction. How does it work? It is very similar to like anything that they have for 802.5. It is a competitor of 802.3, so they are very similar. In here, they want to have a hierarchy of like switches or hubs, okay, and then you have bridges, and you have other technologies interconnected through these hubs with them, okay. But the important issue is that if you have Ethernet coming in, this is a hub, this is not a switch, and it's not a bridge. You can have 100 VG any LAN at the other end. But generally, if you have a hub, you cannot have 802.5 and 802.3 at two sides. See, hub is shared with the same protocol. But in here, they have tried to adjust it that with the same hub, you go through both of them. Anyways, this is the overall, in fact, picture. So you have some LANs. You can put bridges, change the protocol to 802.5 and come here. You can come directly with Ethernet to that. Okay. Now, one important issue, as I said, that is not bad to look into that is the priority scheme. DPAM has priority while Ethernet does not have. We are interested in priority because of quality of service technologies. So how do they implement the priority in here, in the DPAM? In the DPAM, the way that they do the priority is that they tag the terminals in two, in fact, two sort of wheels, if you want to call it. Okay, two timers, if you want to call it. Okay. One is for priority, high priority. One is for the low priority. So the way that it works, the medium access control works is that you have this box. If you want to transmit information, you inform the box that I want to transmit information. Okay. But when you want to inform the box that you want to transmit information, you have two choices. You can say that my information is high priority or low priority. Okay? And then, according to that request, you're going to have the time slot, or the token, if you want to call it. To just clarify that, we start with this example. This example is like, I have these two wheels, and I have a bunch of users in here. 1, 2, 3, 4, 5. These are different users. the box is pulling each of them one after another, in a sense, through the token, or give them a chance one after another to come to the network. Now, what will happen is that, well, maybe it's good to just show you that in here. For example, this is a hierarchy of the switches that you have. Okay, the hierarchy of switches, you first start this guy, then you come in here, you go to this one, then you come and you go to this, this, then you come back to this guy, then you come back to this, then you come back to this guy and this guy. This is how the token gets distributed among these guys. Now, but the point is that each of these terminals are connected to the hub. When they are connected to the hub, they will tell the hub that they are in the idle mode or in information transfer mode. When they want to go to information transfer mode, they can put a signal in here which could be high priority, could be low priority. Okay? And then this guy is always turning around. Okay? Now, so this example is going to describe what is going on. At the beginning, the first demand which comes in the box is coming. This is the time, and these are different terminals. These are the packets. These are the demand. Demand for having the line. Okay? Now, that's the time that you go to the you put a signal on the box. That's these arrows in here. Okay? And these are the actual packet. So, and the box is just circulating around. Box sees a demand from what? From terminal number 2 for low priority data or for normal priority data. Okay? At that time, there is nobody else in there. Assigns the time to that guy. That guy sends the packet. And when it's finished, others have chance. Okay. Now, while this guy was on, two other demand comes in. One is coming from terminal 1. One is coming from terminal 5. And both of them are high priority. Okay. Now, when this one is finished, now terminal starts the second wheel. When you have high priority, you go from first wheel to the second wheel. Okay? So you start to go over what? The first one for the high priorities. First one for the high priority sends this packet. While he's sending this packet, now you have a demand from low priority in the same one, demand for low priority for the third one, demand from low priority for the sixth one, demand for low priority from the seventh one. How should you schedule those? After this high priority is finished, then the turn, still the wheel is high priority wheel. Okay, the high one. You did the 1, there is nothing, 2, 3, 4, you go to 5. So you send the fifth one. Okay, now you don't have any high priority left. Okay, so you have to go back to the original wheel. Original wheel was where? Last time you send in here. Okay, so original wheel is now is the turn for 3. You come for the 3, you send the packet after the packet of the high priority. Okay, after this one you come to the next one. There is nothing. For the next one, there is nothing for low priority. For the next one, yes, you have something with priority, you send it with low priority. And then after that, you come to this one, you send another one. Now, when you are sending this packet, 2 more demands comes in. One is for high priority, one is for low priority. As soon as this guy finished, since there is a demand for high priority, you go back to your previous wheel. Okay, previous wheel, which is the high priority wheel, was in here, finished in here, actually was in here. So comes in here, there is nothing, nothing, sends this guy. This one is finished, goes back to what? To the low priority wheel. Was this one last time, so now it's the next one in here. And then it comes all the way back. First one doesn't have, comes to this one. Clear?
May I ask something?
Yes.
Why does it send first packet before the fifth one?
First packet?
Yeah, that one. Before the fifth one. I mean, the fifth one sends the signal before, right?
Yes.
So why doesn't it send the fifth one before?
See, the fifth one versus the first one. Because when you go to the wheel, always you start from the first one. Okay, so both of them at the beginning start from the first one. Okay, so you stop one, you turn the other one. And when the other one stops, you come back to the first one. It's a very neat mechanism for a hop-based priority. Very simple, very neat. I mean, we will compare this later on with FDDI priority. You will see that this is much more straightforward and simple. Both of them are using what? Both of them are using token ring. And they are implementing that on the token. This is the so-called access priority. Okay, this is the access priority. And you have two levels of access priority. Okay, now if you have 802.5 packet with user priority of 1 to 7, you have to somehow map it to this or somehow relate these things together. 802.1d gives tables for those type of things. Okay? And who needs these tables? Manufacturers. They have to constantly read these things to make the box compatible with different standards. Okay? So, this is like priority scheme. This was like two-level hierarchy for the demand assignment. And basically, actually, this previous one also tells you about the medium access control, which is a new medium access control technique, which is demand assignment. First you demand, and then they assign. Okay, when they assign, they have priority in it. Okay, so that's the whole thing in new MAC. Then the next one is that how does it work? Anyways, we are interested in what? Now, physically, how do you implement this thing? At the physical layer, and also implementation of the MAC layer. Okay. What they do is, remember that this is a competitor for what? 100 base T. And in 100 base T, how many wires you have? You want to be for Cat3. If you want to go for Cat3 and 100 megabit per second, you need to have more than 2 pairs. So you have like 4 pairs. Okay. So naturally you want to use, but you're using your 4 pairs differently. And again, this is hub-based. This is hub-based. Means hub and spoke. Okay. Okay, how do they do it in here? This is how they do it. They did these 4 wires that you have, okay? And these are your nodes. Always, before you send the information, 2 of them go in this direction, 2 of them come in the other direction. What they do in these 2, they can have different signals, 2 levels of signal, low and high, 1 and 2 if you want to call. With the 1 and 2, you can code. I mean, if I send all 1 in this and 1 in the other one, okay, because each of these guys can do, then it means that this is idle for the node, and it's idle for the hub. Okay, because these are bidirectional. It goes from one of them to the other one. Okay, and then you encode, for example, one of them in 1, the other one in 2, from the 2 wires. You call it, for the node, there is incoming data packet. For hub, there is normal priority request. That's the meaning for that one. If you put one of them 2, one of them 1, among the 2, it means that for the node, it's just reserved for the future, nothing. For the hub, it's high priority request. This is how you signal that impulses that I had in the previous one. Okay. Then, if you have 2, 2, both of them high, if it is at the node, it means that link training request. If it is at hub, it means link training request. Means that I'm out of sync, send signal to synchronize. Okay. So, with these like signals, I can talk between the hub and the node. Based on 2 wires, not 4 wires. Okay. And then I do like this. First, I'm in the idle. idle, idle means that I have 1, 1 in here, 1, 1 in here, 1, 1 in here, 1, 1 in here. Okay? Now suddenly this node number, whatever, this node in the corner wants to send some information. When it wants to send some information, uses these two to send a request. Okay? Request is either 1, 2 or 2, 1. Okay? As soon as it sends it in here, hop detects two voltages which are now coding that there is a request going on in there, either low or high priority. In response to that request, first hop puts silence in here, cuts all the signal, okay, doesn't send anything in these two lines. So there's a period for silence, for the signal to get through, and then after that, all four go into this direction now. So now all four wires are transmitting information. But see, the signaling that we were doing, in the other one, we didn't have, like in 100 base T4, we didn't have any sort of nice structure like this. It's a very nice structure. So you send the information in here, your frame, from the node to the hub. Hub receives it, and now should take it and send it to the other node. When it wants to send it to the other node, at first it sends a signal, says that I have incoming signal. Then node will put silence, and after that, all four wires bring the frame down. Okay? And when it's completed, the frame is completed, everybody back to what? Idle mode. It's very, very nice, has the priority, very clean. Okay? Now, on the other hand, when I want to provide now the 100 megabit per second, if I have like 4 wires, all of them similar, if they are in this format, I cannot have like full duplex operation. That's one problem. But on the other hand, since I have 4 equal lines, I can have 4 equal coding in there. Okay? And the coding that they do is like this. They have 4 lines. Each of them is going to carry what? Each of them is going to carry 25 megabit per second. Okay? While when we were in the 100 base T4, each of them were carrying how much? 33.1/3. Because really I had 3 of them. But in order to go to the 3, you had trinary. Okay? To go to, do you follow that? Do you remember that? Now in here, you don't do that. Huh? You stay with non-return to 0. You stay in the binary. Okay? While in 100 base T4, they go to trinary. Okay? So if I stay in the binary and 25 in here, what I need is, like, I have to use some coding. They use 5B, 6B. Okay? Earlier we had 4B, 5B. Now what is this 5B, 6B? I will tell you a little bit later. It's slightly different from 4B, 5B. Okay? But in the old one, after 4B, 5B, I was going to what? 3 levels. In here, they don't go. Okay? But in order to make this signal a little bit better, before they go to 5B, 6B, they put a scrambler. You remember that? Scramblers are going to help you in increasing your synchronization, improving your synchronization. In a sense, improve your channel. Okay? Either you change the levels, that's a little bit help, or a scrambler, that's a little bit help. They get that little bit help in here from the scrambler. Okay? And we didn't have a scrambler for 100 base T4. And then they add a delimiter, and then they go to non-return to 0 encoding. And that's it. That's what they do. And each of these are 25. Okay? Now, the only thing which is vague in here is what is this coding? And what is the difference between this one and let's say 4B, 5B? Okay. The coding in here is in here. If you remember, in the 4B5B, you were ensuring 2 transition, okay, per each 5 bits. In here, what they do is actually, they say that I have total of 5 bits. With 5 bits, I have how many symbols? 32 symbols. I'm encoding that to 6 bits, okay? And the 6 bits that I have in here are 64, okay? What they do is they come and divide the 64 in 2 sets, actually, and they alternate. How do they divide it to 2 sets? For example, 0, 0, 0, 0, they assign 0, 0, 1, 1, 0, 0, and then they have another complement of that, which is 1, 1, 0, 0, 1, 1. They alternate. First time, if it's 0, 0, 0, 0, they send this. Second time, they send this. As a result, on the average, you have how many? 3 transitions. Okay. What did you do in the 4B5B? In the 4B5B, I took these extra things and I used some of them for idle and like other like control signaling. One of them was idle. Huh? In here, they don't need that because they have implemented it already with the mechanism that I told you in the previous one. In that coding of 1-2 coding. So all 64 are available. So they divide it in 2 and they give it to them. This way they avoid the DC offset in there. Okay? The code are balanced all the time. It's still very nice, very clean. Okay? So if you look at all of them, it's like that. Okay? They try to put so that they have this average number. They are not complement all the time. For example, in here, you have 10110, 10110 repeated in both of them. In here, you have 130. In here, you have 3 ones and 3 ones again. Because for 3 ones, you don't need to compensate again. This one is 2 1, the next symbol is 4 ones, etc., etc. They come down and fill up this table. Okay. So that was more or less all that I wanted to talk about in DPAM. One was, we talked about the MAC and how they implement the priority in that MAC. And the second thing that we wanted to discuss was the physical layer, that rather than 3 strange wiring, they have a very structured wiring. They don't have trinary. They have binary. And they use a scrambler and this coding, which is better actually, 5B, 6B. Looks better than what? 4B, 5B. Yes?
Cat3 is 16 megahertz. That makes it 16 MPS at most. And we have a 5B, 6B, which makes it 5 by 6 of 16. That's somewhere around 40 by 3. How do we go to 25 megahertz on each of these?
For the 25 meg, how did we go to the 25, you said, huh? For the 25 baud. I think in here that's the scrambler which helps them to go all the way to there for the wires. Good question, very good question. I will think about it more. If I find something other than a scrambler, I'll tell you next week. I think that's because of the scrambler. Okay. Now, the next one is like FTDI. So did you follow his question? He says that if you're going for Cat5, you can go 16 megahertz. How do you go from 16 megahertz to 25? Okay, how do you stretch it? But part of that you have to, part of that is because of this coding, 4B, 5B coding. Because on Cat3, on Cat3, in terms of like Ethernet, okay, how much you can go?
16.
Ethernet goes 20. When you do the Manchester coding, you go like 20, okay? You go the baud rate of 20 for that, 400 meter. You add a scrambler on top of that, It carries you up to there, okay? Up to the 25 or something like that. And then the overhead of the coding in here is 5B, 6B, which is 5B, 6B is like efficiency is like around 90%. So that's, I think, what they do. So the effect of a scrambler plus that 20, okay, and effect of 5B, 6B rather than 4B, 5B. All of those little things together keeps them at 25 baud. Okay. Now, the next one, the next standard other than PAM is FTDI. PAM, as we said, was 1995. FTDI is 1985, 10 years earlier. FTDI was the first 100 megabit per second standard. And when it was standardized, it was to operate in fiber. But later on, they extended it to the copper as well. But the standard is called Fiber Distributed Data Interface. So FTDI. So some people, when they go to copper, they call it CDDI. Some people, they don't. Okay. But you should note that FTDI also works on the copper. Okay. In spite the name. Because that copper addition started around 1990s, something like that. Later on. An overview of the FTDI. One more interesting thing about FTDI is that now we are talking about the LANs and everybody was under IEEE 802 community. FTDI is the first one which was done by ANSI. ANSI was American National Standard Institute. Okay, and this is the name of the document in there. That's ANSI X3T9.5. That's the name of the document in ANSI. If you remember, IEEE people were designing the standard, then they were going to ANSI. Okay, IEEE is like a specialized group. ANSI is representative of a country. That's legal. I mean, legal may not be the correct word. It's like national standard. Okay, the other one is like recommendation. Okay, that's the difference. Now, then the main part was approved by ISO and IEC, which are the international organization, in 1990. The unshielded twisted pair physical layer was adopted by ANSI in 1995. Okay. Now, original goal was to provide 100 megabit per second fiber to every desktop when they started. Because a start was around, as I said, research. Actually, my research in local area networks was 1981 at GT Lab, was about fiber local area network with wireless drop. That's when I started my wireless work. So early in the 1980s, people were doing research to implement FTDI. In 1990, it becomes a standard. Okay? But you have to consider that in that period that it was evolving again, fiber was the hype. And they wanted to bring it to the what? Desktop. Okay? Fiber to home, fiber to desktop was all over the place. But high cost of import and other difficulties stopped development of that market. Because they already had problem to place the cables. And fiber is more delicate than the cables. Okay? That could be one reason. Today, when it became to the market, appeared into the market, which was actually before the standard, actually, before 1990, people were using that as backbone. In WPI network, if you remember, the one that we established around 1986, around that time, backbone was FTDI. Okay, original one. But more recently, they have changed that to what? To gigabit Ethernet. which is changing everything. And in between, they changed it to an ATM. In mid-90s, they changed it to ATM for the backbone, because the moods are changing as the time changes. Now, still there are like FTDI installations here and there left over from the past. The Mac is a sort of 802.5, but it is a little bit different from 802.5. In 802.5, if you remember, you had this token ring that you send a packet, and packet, you wait, okay, for the packet to go to be read, come back to you, and when it came back to you, you send the acknowledgement. In here, as soon as you send the packet, you will send the acknowledgement. Now, what would be the effect of that, impact of that? Impact would be that now you can be faster. You can have a better throughput. Okay? Because you don't leave the thing, you don't leave the ring empty, okay, for a long period of time. Anyway, this is 100 megabit per second. Packets are relatively shorter now, but they are going faster. Okay? So as soon as the packet went out, you send your acknowledgement so that there is less idle time in between and your throughput goes up. What is the penalty in there that you play? Penalty at the implementation of priority. You remember how was the priority in 802.5? You were sending the packet, it was passing through the other guy was changing a bit that I want to pick up the next priority item. Huh? But in here you cannot do that because already things is in the air. Okay, so you have to have a new mechanism. And we will go over that mechanism a little bit later. Okay. Then physical layer is the same as 100 base X that we discussed earlier, which is first is a 4B5B coding, followed by what? Followed by ML3. If it goes over the wire, and if it goes, I mean, the wire in there is shielded twisted pair or Cat5. Or if it wants to go to fiber, after 4B5B directly goes to fiber. Okay, that's the same in here. This is like a sort of block diagram which shows different layers. They have this MAC layer on top, and then they have physical sublayer, and before physical medium dependent sublayer. That's the last one in there. Okay. Physical medium dependent sublayer is the one that really has this filters to read the inbound and filters to read the outbounds. Reads the light, okay, and turns it to the bits, okay. And then they have the optical bypass switch, which allows you to go in both directions in there. And then you have optical receivers and then the optical transmitter in here, okay. Then you have in here synchronization, clock recovery. Clock recovery in here is more important than 802.5. Why? Because you are going 10 times faster. The issue is that when you have a token ring and you have faster transmission rate, okay, you need better synchronization. In addition to that, FTDI is running over longer cables, okay. As a result, this timing recovery becomes what? More important in here. But anyways, it is in there. That's the timing recovery, thanks. The clock that you have, similar to 802.100 base T, this is 125 megahertz clock, which supports the 4B5B to provide 100 megabit per second data rate. Okay, and this is the decoder, this is the encoder. Okay, so this is a good view of like a transmitter receiver node for any fiber, any sort of fiber installation. We didn't have it before, But since this is FTDI, that's the appropriate time to have it. Next issue is the issue of counter-rotating ring in the backbone. You have to remember that 802.5 was for connection to terminals. This is connection to the backbone. Failure in the backbone is less tolerable. You want the backbone to be more reliable. As a result, when they were doing the standards from day one, they were talking about dual cabling. So you have two rings actually inside one ring. One of these two rings is your reserve ring. And that's used for the time that if a part is broken, it will loop back. And then you have the rest of the terminals together. Okay? So this is another addition that they have because it is the backbone. Okay. The next issue is that if you have FTDI and you want to go over wires, you have to go over unshielded twisted pair Cat5, okay, or shielded twisted pair. Okay. Now, how do you do that? They have a hub in here, and they come and they go back, come and they go back, come they go back, come they go back. This is like the wiring that usually they use for what? 802.5. It's very similar to that. Okay, but these are not like dual. These are single. Okay? The other one that I had previously was dual. It had like two connections. One as the backup, one as the regular one. As a result, in FTDI, they had to support both single and double connections. So they had to define some sort of like nodes and connectors, okay, which operate for single and operate for double. Okay. They have done that type of thing like this. They have dual attachment connector, single attachment, and single attachment connector. Connector is the one which wants to hook to the ring, okay? And attachment is the terminal itself. Okay. So they define like 4 classes of, if you want to say, elements. One is like DAS, which is for dual attachment, and then they have like dual connector, they have single attachment, single connector. With that, they can have a network which not only can be used for the backbone, can also go to the terminals. For the backbone, you want to have a dual ring, okay? But for the terminals, you want to have a tree, okay? With these elements specified in the standard, you can implement networks which are mixture of the both. For example, you have a connector in here. In one side in here, you have terminals which are only single, okay, single station attachment. And in this side, you have dual attachment station. So in one part, you have dual attachment. In one part, you have single attachment. And if you go to a more complex network, then you can implement something like this, which is really a ring tree topology. Okay? So in the ring, everything is dual attachment. Everything is DAC, dual attachment, which connect point to create the ring. Then one of these dual attachments comes down to what? 2 single attachments. Then you have single connector in here to extend this line, single connector in here to extend, and then you have single access over in here. So the picture that they see overall is a ring tree topology. rather than only ring topology. Okay. Now, in reality, however, this part mostly were in copper and often not using FDDI, using Ethernet. Okay. Because when you go to Ethernet, the terminals are going to buy what? Less expensive connector. I mean, NIC card. Okay. As we said before, if you want to compare it with 100 base X, 100 base X is using the lower parts in here with CSMA CD. In here, they use it with their own MAC, which is a token ring. Okay. If you want to compare FDDI with 802.5, basically data rates are different. That's the most important thing. Size of the packets are different. And coding is quite different. I mean, physical layer is quite different. In 802.5, you have a sort of central station to cover everything. In here is distributed. Okay. The type of priority in here and priority in here are different. Okay. And the last but not the least, in FDDI, you release the token after transmission. In here, you release the token after completion of the packet when it comes back as an acknowledgement. Okay. So these are some differences between them. The only thing which is left now is advantages, disadvantages, and how they implement the priority. Now, advantages, more or less, we talked about that earlier. Number one, when FDDI came in, it was covering longer distances, and it was fiber, immune to electromagnetic interference. And then it had a good throughput because it is like a deterministic. Token ring is like deterministic. It's not random, in a sense. Half deterministic, if you want to call it. And station managements are a little bit more difficult in the term of 802.5. Now, then the next thing is like handling of the token that we have seen that before. Token comes right after the packet. Because token comes right after packet, my priority scheme is not going to work the way that it was working before. So what is the packet format? The packet format is very similar to the packet format of 802.5. In here, I have preamble. In there, I didn't have preamble. Why do I have preamble? Because in here, I'm talking about higher data rates. For higher data rate, I need to reduce my jitter. In another word, I need to have more synchronized stations. Okay. Now, but more or less, the rest is very similar to 802.5. In here, I have talked about the changes or differences that they have. Basic differences that you have for the frame of 802.5 and FDDI is the preamble. The next one is in the FDDI, priority and reservation bits are not there. Okay, and FDDI handles capacity allocation a little bit differently. Oops. Priority of 802.5, we said it. You send the packet, goes through, and people change the token. Now, what is the priority in here? How they implement the priority? This is the last thing that I would like to cover in FTDI. And you also have a homework related to that, so I go over the detail of that. In here, when they handle the token, the way that they handle the priority, first of all, they differentiate synchronous and asynchronous, voice versus data type of applications. Okay. So when you come, you have like two sort of data. One is synchronous and one is asynchronous. Huh? Now, data and voice. Okay. And then you take the time, when you come to a terminal, you give priority. There are times that you will send either synchronous or asynchronous. There are times that only you send the synchronous. So there are times that you only send voice-oriented data, or they call it time-bounded information, and there are times that you send both of them together. Now, how they have implemented that mechanism? Because in the Mac, they don't have anything to support that. Okay. The way that they implement that, they have to implement it in the stations. And to implement that, they are using three actually sort of timers and counters. Timers are counters, really. One of them is a binary or late counter. This counter is the one that will tell you that you are allowed to send both type of traffic, or you send synchronous traffic. Okay. So it says that, so if you have data, you keep it, if that's not a good time to send it. But if it's voice, you send it right away. Okay. So I have a counter to say that whether this one or that one. Okay. The second thing is that now, to check to see that what is going on in here, they have a couple of counters. One of them is token rotation timer. The other one is token holding timer. And based on those two, they implement this algorithm at each node, okay, which handles the priorities. At each node, and this is the example, which provides an overview of that mechanism. This example is coming from the book. At time A, token comes to this terminal that I'm right now in it. Okay. As soon as the token comes in, I will start counting down. I start from the 100 time slot, and I start to come down. Okay. At time B, and at this time I didn't have any information. So I send the token to go, and I start counting down. And then 60 microseconds later, token comes back. It has gone to all the terminals, comes back in here. As soon as the token comes back, this time I have some data, synchronous, some data which is asynchronous. Okay. As soon as it came back, I go the counter again to the 100, start to count down. I send my synchronous data, okay, and I send my asynchronous data. But this asynchronous data is sending leftover of this time. When this leftover is finished, I have to stop it. Okay. At this time, synchronous is finished. At this time, asynchronous is finished. This timer, which was the big timer, my major timer, TRT, this is coming down all the time. Comes down all the time, and after this time, after 100 milliseconds after the 60, this time expires because this counter was for 100 milliseconds. When it expired, it goes back, it starts to count again. But since between the last one and this one, he had not received any token, it changes this pointer to the case that I'm late. So don't send asynchronous anymore. Only send your synchronous. And this way they continue. Okay? Now, this example, yes, gets, yeah.
How would we differentiate, like how long we're supposed to send the synchronous and the asynchronous? Like for 30 milliseconds he was sending the synchronous.
We have a good example next one in the table which shows how it works. This is the table which has the same thing in more, another example. You have 4, this time a station. The first one was how each station behaves. This is behavior of 4 stations. Okay. This is a station 1. It starts at time 0. Token arrives at time 0 in here. And he has nothing. No sync, no async. So it sets the clock, that TRT clock, to 100, and it starts to count down. Token at 1 slot after that comes to station number 2. This guy sets the clock in 100. He doesn't have anything. Next slot token comes to the third one, sets TRT to 100, has nothing. Next one comes to fourth one, the same. He has nothing. So in the first row, nobody had information. So each of them, they kept the token for 1 slot, and they initiated the TRT at what? At 100. Second round, when it comes in, now clock is at 4, slot number 4. Since it is at 4, this was originally 100, it has come down to 96. Okay? Now it sets it back to 100 from 96. Okay? But looks to see what it has. It has 20 synchronous and it has 96 asynchronous. So, since this clock was 96, he can send the entire 96. First it sends the 20, then he sends the 96. He sends the 20 and 96, plus 4 is 121. Plus 1, which takes for the token to go to the next one, is at time 121, it goes to the next terminal. When it comes at 121 to the next terminal, the total time was how much? More than 100. So this guy has come to the 0, again has gone to 100, come back to what? 80. Come back to 20. Come back to the 80. But since it was more than 100, that flag has gone up. Huh? So when the flag is gone up, I have a star in here. Only I can send synchronous. He sends the synchronous, which is 20. Clock goes to 142 when it arrives to here. What is the difference between these two? Again, 140. So my clock in here has gone 100 down, has gone to the 100, has gone to the 60, and it's in the star mood. Means it's late. Okay? And then he has synchronous, he sends it. But it cannot send the asynchronous. Okay? Comes to the next one, the same. Comes next time in here, this time, this guy is what? A star. Again. Since it is in a star, it cannot send the asynchronous. Goes to the next one. Next one is a star. It can send the thing. Continues. This is a star, only synchronous. A star, only synchronous. Comes, this thing continues up to here. When they come in here, suddenly it's back to what? To the non-star. Means that token has arrived early now. Why? Because the difference between these two is less than 100. When token left, until token comes back, is less than 100. Now, he can start sending what? 12 bytes of its asynchronous queue. Okay? Because there is 12 left in here. Cannot send more than that. Send this 12, comes to the next one. Next one is in the star mode, cannot do anything. Star mode cannot do anything. Okay? Comes to the next one, star mode cannot do anything. Comes to here. This one, clock is 385 minus this less than 100. So, how much clock is left? 4. So it can send the 20 plus this 4. Okay. Comes to the next one. This 2, the difference is more than 100. So it's in the star mode. Only sends the synchronous. etc., coming. Did you follow that? So basically there are two mechanisms in there. When the clock goes, this is the timing. Clock goes, clock comes back. Token goes and token comes back. You measure that if the token between going and coming back was more than a given time, which was 100 milliseconds in this case, okay? It was more than that, you're late. If you're late, forget about asynchronous. If you're early, you can only use leftover of the token time for the asynchronous. And this way, they have this mechanism, which works. Okay? This is again another mechanism, a very good mechanism actually, for what? For automated enforcement of what? Priority. This is differentiating voice from data. A mechanism like that, you can take and modify that a little, use it in Bluetooth, for example. Okay? Or other places which are needed. Okay? This is like access priority, providing access priority. Okay? It's a method to provide access priority. And at the same time, differentiating the traffic from the voice, for the voice and data. That's one mechanism. Okay, and you're doing that through what? Through terminals themselves. The terminal itself has like these 3 timers. In particular, 2 of them are very important. Based on that, you're tracking and you're enforcing something in there. Okay, a sort of priority in there.
Does this kind of a technique put a limitation on the number of stations we can have in the ring? Because
all of them, they have limitations. FTDI has limitations on the numbers too. Yeah. But the limitations on the numbers in here comes earlier because of the jitter. See that phase-lock loop that they have collects, minimizes the jitter, but jitter doesn't die. If the jitter for the whole ring becomes more than 1 bit, that's it. You cannot go longer than that. So they calculate that and they put it in. Now, so this is the story of the FTDI. The last one that we want to talk about is asynchronous transfer mode LANs. This one, apparently, we cover in the next lecture. This is basically about ATM itself. That part which is about ATM is about switching, really. We talked a little bit about switches earlier, and we are going to have another lecture on bridges and routers, which are in the same category as bridges. Okay. And then after that, after one brief introduction of ATM switches, I will talk about ATM LANs. We had a little discussion on that earlier. And the importance now of ATM LANs, what is, to my opinion, important about ATM LANs, that's the place that you can unravel the differences between connectionless and connection-based networks. How you can have mixed connection-based and connection. Today, all the networks out there are, in spite all the desires in the past 10 or 20 years to make it one network, it's no one network. Part of the networks are connection-based, part of them are connectionless. Even if you are doing like an IP application and you're working from here and you're sending an email to Finland, somewhere in between you may have ATM, which is connection-based. Okay? Now, so we come back to this thing as that connection-based part of our lectures. And connection-based comes. One is the issue of switches versus bridges and routers, in which addressing is important. Okay, when you go to the connection base, you have establishment of the time to create the connection. But when you created that connection, now you can have very short addresses. So address that you had, for example, for the IP address, version 4 was what? 32 bits. For the MAC address was 48 bits. In here, you have like 16 bits, short addresses. The other thing that they have in the ATM, which is important, is that they keep the packet length fixed, as we discussed earlier. Now, if the packet is fixed and the header is small, when the packet arrives to the switch can immediately do the switching. But if the packet is long, like IP packets or MAC packets, you don't know how long it is. Okay? You have to read the entire thing before you start to doing the switching. Okay? So as a result, these are faster switches. Another advantage is that since they are connection-based, at the beginning I'm establishing the line. When I establish the line, I have that quality of service enforced. Okay. So we will talk about that in the next lecture in more details. I'll see you guys next week.